Alright, next topic, kinetic and static friction. Both of them are friction, so the equation for calculating the friction force are the same, which is Ff, the friction force, is equal to normal force times mu. What is mu? Mu is a coefficient for friction. Mu can be bigger if you're on a rough surface, and mu can be smaller if you're on a smooth surface. It depends on the situation. And the range for the mu will always be smaller than 1 and bigger than 0, not inclusive. Also, I have to mention that the kinetic friction, which also known as sliding friction, is like a friction when the object is sliding. Will always be smaller than the static friction. A static friction is basically an object, and there's a force pushing it, and it stays at rest, which means it is at equilibrium. I would just use EQU. It's at equilibrium. The force that balances it is the friction force, and this friction force is the static friction. So the kinetic friction will always be smaller than static friction. And now let me give you some sample problems to actually calculate the friction force. An object is on a horizontal ground. Yeah, this is a horizontal ground, although it looks very ugly, with a mass of 2 kilograms. And it's stationary at rest. The coefficient mu between the bottom of the object and the ground is equal to 0.2. And it's asking you what is a static friction. Okay. First of all, let's draw a free body diagram. This is a dot, which represents the center of mass of the object. The first force to act on it is definitely gravitational force, which is Fg. It's pointing downward. Also, in the question, it said the object is at rest, which means it is equilibrium, which also means the net force of this box is equal to 0. We already have an Fg, so this object definitely has a force that has the opposite direction as the Fg, but has the same magnitude as the Fg. What is that force? Yes, you're correct. It's the normal force. In terms of magnitude, Fn is equal to Fg. However, just a reminder, if it's asking you the vector Fn is actually equals to the vector Fg, because they're in opposite direction. Negative Fg, my bad. So what is Fg? Fg is just mg. It's equal to, what is the m? 2 times gravitational constant, which is 9.8. This is 9.8. It's equal to 19.6. 0.6 newtons, which is equal to Fn. Okay, now we figure out the Fn. Well, how do we get the friction force? Yeah, using this formula. So Ff, the friction force, is equal to Fn times mu, times that constant, times mu, which is equal to Fg times mu. We already get Fg, which is 19.6, which we can plug the number in, which is 19.6, times, this is times, what is a constant? The constant is 0.2 right here, so let's plug the number in, times 0.2, which we can get, I think it's 3.92 newtons. Don't forget your unit for the forces. That's it. That's how you calculate the friction force when the object is stationary and on a horizontal surface. And now you may ask, how do we calculate the friction force on a slant surface? That's easy, so let me tell you. This is a surface. This is a sloped surface with an angle theta above the ground. There's an object on this surface with a mass m, and it's at rest. Asking you, what is the friction force of the object? First of all, let's draw a free body diagram. This is the center of mass of the object. The first force we're going to draw is gravitational force, because every object has gravitational force if it is on the Earth. The second thing we have to draw is normal force. The normal force will always be perpendicular to the surface it touched. In this situation, the surface the object touched is actually sloped. So the normal force will be pointing this way. Will be pointing this way because in order to make it perpendicular to the surface. So let's draw it on our free body diagram. Also, it is pointing upward because the surface give it is pushing it upward, right? In order to stop it from falling, in order to stop it from going down, right? So this is normal force. And then the third force we're going to draw is friction force. The friction force will always be in the opposite direction of the motion. So imagine this. If you put an object on a slammed surface, it will going down. It will or rolling down along the surface, right? So in this situation, if there's no friction, it was sliding down in this direction. This is also the direction of the motion, which means the friction must pointing that way. So this is the direction of FF. Now you may ask, how do we calculate the friction force on a slant surface? Well, that's not hard. Let me tell you. This is a slope or a slant surface with the angle theta above the ground. This is an object, which stays on the surface obviously. It has a mass m, and it is at rest. How do we calculate the friction force? Well, FF. First of all, let's draw a free body diagram. Let's draw a dot first, which is the center of mass of the object. The object has a gravitational force, which will always pointing downward. And the next force we're going to draw is normal force. The normal force will always be perpendicular to the surface it touched, which in this situation is this surface. So it will be like this. It will go like this direction, which enables it to be perpendicular to the surface. Also, it will point upward because the surface stops it from falling down. So let's move it to our free body diagram. It is pointing upward. This is Fn. Now, the next force we're going to draw is friction force. The friction force will always be at the opposite direction of the motion. Imagine this. If there's no friction in this situation, this box or this object will sliding down along the slope or along this surface. This is the direction of the motion, which means this, the opposite direction, which is this direction, is the direction of the friction force. Let's draw the friction force on our free body diagram. This is friction force. Also, we can get normal force is perpendicular to the friction force because this friction force is parallel to the surface, and the normal force is perpendicular to the surface, which means the normal force will be perpendicular to FF, to the friction force, which is parallel to the surface. So what we're gonna do next? What we're gonna do next is break those forces into components. As we can see, there's already a 90 degrees over here. So let's draw an axis like this. Let's break the Fg down because Fg is a force we know. So this is the axis, this is Fg, this is Ff, this is Fn. How do we break it down? So let's draw a perpendicular line, a dotted line, to the FF direction. And then this is one of the component. This is another component, right? And then how do we know the angle? Because the FF is parallel to the surface, which means this is actually theta. I draw a little bit awkward, but yeah, this is theta. But I want you to just remember this angle will usually be theta. Will usually just be the angle of the slope I don't want to prove it because it's a little bit complicated, but just remember it. All right. This this is one of the components. This is another component because Fn is parallel to this direction, to this component, which means this is also theta. Then let's use our trick. What is this component? This component is just Fg, which is this, times sine theta. Component number one, I'll just use component. Component number one, it is Fg times sine theta. The component number two is Fg times cosine theta. Oh, by the way, this is component number two, and this is Fg. Well, let me draw it again. Actually, this is Fg, this is Ff, this is Fn. Let me make it clear. Ff, Fg. Make an axis. This is theta. This is component number one. Oh, this is also theta because, yeah, this is perpendicular. If you know geometry, you can easily get it. This is component number one, C1. This is component number two, C2. Yeah, now you can see it clearly. Then, because I said that it is at equilibrium, which means each direction the net force is equal to zero, let's look at the normal force direction first. The normal force direction, I would just use it, write it down, the net force equation, Fn, no, just net force F1, yeah, F1 is equal to Fn minus the component number two, I'll just use FC2, it's equal to zero because it is at rest, it is at equilibrium, which we can get Fn equals FC2, which is equal to component number two, which is Fg times cosine theta. Now, let's look at the friction direction. Let's write the net force equation for that. Net force number two is equal to Ff minus C1, component number one, Fc1, which is also equal to zero because it is also it is equilibrium, which means each direction, the force on each direction, the net force on each direction must be zero, and this is a direction. So Ff minus Fc1 is equal to zero, which we can get Ff minus Fc1 is equal to Fc1, which is equal to component number one, which means it's equal to Fg times sine theta. Also, what is Fg? Fg is equal to mg, which means the Ff is equal to mg times sine theta. This is a friction. Oh, also, by the way, I use minus over here. It's because the component number one has the opposite direction as a friction force of the friction force, and the component number two has the opposite direction as normal force. So I also use minus over here. However, if they're at the same direction, you will use plus. Like if it is at the same direction, like this is the Fg. No, wait, let me see. This is Fg. This is applied force, like you push the object. This is applied force. You will use the net force equation. Fa is equal to, the net force equation is just equal to Fa plus Fg. Yeah, that's it. That's all for this topic.